All right. Can you guys hear me? Yes. Cool. So good morning and welcome to this talk. It's great to see so many people interested in what we have to say. So my name is Erica.
I'm Vladimir.
And we are software engineers at Spotify. We work in the ATC team, and that's the team that owns and operates Spotify's perimeter. The perimeter is on the path of each and every communication between clients and Spotify's backend. And so for that reason, it's a very critical piece of infrastructure, as you can imagine. Spotify adopts an ops in teams model, meaning that a team that develops a service is also responsible for operating it 24/7 in production. And our team is no different. So on a daily basis, we deal with both operational kind of work, which just stems from keeping the lights on, so to speak, but also with development work, which has to do with how we decide to evolve the perimeter over time. In our team, we also have an on-call rotation, which is on a weekly basis. We are here today because we want to share with you how we migrated a part of Spotify's perimeter to an Envoy-based solution. Of course, we will explain how we did it and also share with you what worked well during this work, what didn't, so the lessons that we learned along the way. And also, we will briefly talk about our vision for Spotify's perimeter moving forward. Finally, we want to leave you with, let's say, the key takeaways from all of this migration work that we've done, with the hope that they might be useful to you if you're going to do similar migration in the future. Hopefully, the majority of you in the audience is familiar with Spotify, has heard of it before. Even better, you're a user, or even better, you're like a paying user. But just in case, let me quickly say what Spotify is. So Spotify is an audio streaming platform, and it's available on a wide variety of devices and clients. Spotify has 248 million monthly active users, making it the most popular audio streaming subscription service. As you can imagine, all those users generate quite a bit of traffic, but just to give you a more precise idea of the volumes we're talking about, at peak, Spotify's perimeter handles more than 8 million requests per second. Spotify's backend is a distributed system, and it has a microservice architecture. We have more than 1,000 microservices deployed in production. Also, nearly all of Spotify's services and infrastructure is hosted in Google Cloud, and we are present in 3 regions, one for Europe, one for the US, and one for Asia. But let's now see how the backend, the perimeter, and the clients all fit together to make Spotify work. So on the right-hand side of this diagram, you can see Spotify's backend. And like I just said, it's made up of many services. Of course, some of these services, like, for instance, the login service or search or playlist, have to be exposed to the public internet so that your smartphone or whatever other device out there can actually talk to these services when you're using Spotify. And that's exactly where the perimeter comes in. It allows exposure of backend services to the internet so that clients can communicate with them. But it also acts as kind of a wall, a protective wall between Spotify's backend and the internet. But let's now zoom in a little bit more on the perimeter itself. This diagram is somewhat of a simplified view of our perimeter, but it still kind of serves to illustrate the main use cases for the perimeter. The first one is represented by the vertical on your left-hand side, and it's to basically allow HTTP clients on the internet to communicate with backend services that only understand Hermes. Now, if you've never heard of Hermes before, that's totally fine, because it's a proprietary protocol that Spotify developed back in 2012. And though it's now being phased out in favor of gRPC, we still have a lot of services that use it. So the perimeter has an HTTP to Hermes gateway just dedicated to this use case. But Spotify's backend also has quite a bit of services that talk HTTP. So in that case, the perimeter has a web gateway that you can see in the middle of the diagram for these HTTP clients to HTTP services use case. And finally, one more use case served by the perimeter is to allow persistent connections between Spotify's backend and clients. And that's to allow state changes that originate in the backend to be pushed out to all the connected clients. So a typical example of this would be if a new track is added to a Spotify's playlist, for example. This talk is going to focus on the part of the perimeter that is highlighted by the red box, so the HTTP clients to HTTP services use case. And it's going to cover how we removed, or let's say replaced, this part of the perimeter with an Envoy-based solution. Now, Vladimir will zoom in a little bit on this red box and explain what's inside.
Let's dive into our old perimeter. Public DNS has the IP address of the Google TCP load balancer, and our web gateway sits behind it. Each web gateway, we call it WebOB internally.
There's no.
Is it better? Each web gateway, we call it WebOB internally. It's a host in Google Cloud with Nginx for SSL termination and proxy into HAProxy. HAProxy is responsible for balancing the load among a set of backends. And HAProxy is
Thank you.
Sorry. So each WebOB is hosted in Google Cloud with Nginx for SSL termination, which proxies to HAProxy. HAProxy proxies to backends, and for example, the backend which handles the traffic for www.spotify.com. For each URL, www.spotify.com, the account Spotify.com, there are multiple exposure settings, like request timeouts, how to health check, overall like 25 different things. The Puppet is responsible for configuring both the Nginx and the HAProxy from configuration from GitHub. Service discovery was also done by Puppet. Each Puppet was run continuously, and it resolved the backends from our service discovery system. Each Puppet run updated configuration file for HAProxy with IPs and ports for the backends. When Spotify developer wanted to expose a website or an HTTP upstream, they made a pull request to a Puppet Git repo in a single configuration file. So let's see if there was something to improve. The old perimeter had some flaws, and those became apparent as time went on. In the past, Spotify prioritized mobile traffic over the web traffic, and that made the old HTTP perimeter kind of obsolete, kind of an afterthought compared to the traffic which was coming from the iOS devices and Android ones. Features were added over time, sometimes haphazardly, and the HTTP perimeter became kind of obsolete. With the available features were not relevant, and the relevant features were not available. Things were so bad that the product teams were running their own perimeters based on Nginx's and even on Envoys behind our perimeter and before their backends to get the needed features. The old perimeter was incident-prone. There were serious discovery problems, like a Puppet run took around like 5 to 10 minutes, and that put a limit on how fast the new backend could be discovered. And that in turn was a big issue because like Spotify, all our features and product teams move to fast-changing ephemeral infrastructure such as Kubernetes. Our old perimeter was costly to operate. It was like a lot of incident tickets, and in 2018 alone, it was mentioned in 30. It was difficult to troubleshoot because of the poor observability on the HTTP upstream level. We could evolve the old perimeter, fix the service discovery, like add the relevant features, but that would mean that we would invest only in the HTTP to HTTP part of the perimeter that Erika told us about. Seems it's obvious where are we going with this. Looks like we're migrating from it. We chose to unify perimeter under one awesome gateway, doing all things perimeter and based on Envoy, and we called it Edge. All our protocols, HTTP to Hermes, pure HTTP, and gRPC, would need the similar features like authentication, authorization, security features, and metrics, and so on. It makes a lot of sense to implement it once. So migration, sure, but like why Envoy? Spotify overall is becoming more and more cloud native. The core infra department, which our team is part of, is leading the Kubernetes migration. And you could hear the James Wen talk yesterday. Also, we're trying to swap this Hermes protocol for the gRPC. And so using CNCF, it makes a lot of sense to use cloud native take offering for perimeter as well. The perimeter is far from Spotify core business, so it makes a lot of sense to use a CNCF baked one, which has taken off as a standard already. Like it's kind of an easy choice to make. XS protocol allows us to configure our envoys with high-level Java control plane, which with lots of tests and with using abstractions and using Spotify domain terminology. This will allow us to provide a blessed set of use cases to the users, Spotify developers. We call these use cases golden paths. And we would use the same practices and tools that the rest of Spotify uses for development. We also like that Envoy enjoys a lot of community activity, and a lot of companies like ours or even bigger contribute to it. We also want to contribute back, and our team members, they're sitting in the front row, already made a handful of pull requests back to Envoy. So let's see how we're going to redesign the perimeter with the Envoy's help. So this is Edge, our new perimeter system, drawn as a set of boxes. The bigger blue box is the Edge VM. On the VM, there are like a few Docker processes, and the first one and the main one is Envoy, listening to HTTPS traffic, HTTP and HTTPS traffic coming from the Google HTTPS load balancer. It handles both gRPC traffic and HTTP. Envoy, each incoming request is called by Envoy's xauth filter, which passes to xauth service, which runs on the same host. Each xauth service checks the authentication. We currently only support bearer auth tokens. And also it does declaration of the incoming requests with like geolocation data. It matches the IP addresses of the users to the countries and cities where are they coming from. All Envoy instances are configured by our control plane cluster. The gRPC control service, which we implemented, allows us to limit the rich set of things that you could do in Envoy with the set of blessed use cases which perimeter should support. So how did we migrate? Erika will tell.
Right, so pretty early on, we identified the core major requirements for this migration work. First of all, it shouldn't create any additional work for the owners of the upstreams being migrated. The main idea here is that product teams in Spotify should be able to stay focused on developing new product features, and the switch to a new perimeter should be completely transparent to them. The second requirement would be the migration should be transparent to the end users of the upstreams. So in this case, we're talking about a target of zero downtime, or at least as close to that as possible. Third, the migration should happen gradually, and that's for mainly two reasons. Up until that point, Edge actually served virtually no traffic. So while we were pretty sure that it was battle ready, we didn't actually have any metrics to prove that. So we kind of needed to build some confidence in the new perimeter, if you will. And also we wanted to minimize impact on end users in case of unforeseen problems with Edge. And lastly, we should have a quick fallback. So if during the migration at any point something goes wrong and the users are impacted, then we want to have a way to revert back to a working state. And that must happen quickly, within minutes. So we kind of want a big panic button that we can push anytime we even suspect we're in trouble. Given these 4 requirements, we came up with a migration in 3 different stages. So now we're going to talk about each of the stages. The main objective for this first stage was to put some traffic on Edge and learn as much as possible about its behavior under load. We decided to migrate one of the HTTP to Hermes gateways in the perimeter. This specific gateway serves only traffic for experimental features or features that are under development and makes no guarantees about its availability or reliability. So it's kind of less critical compared to similar gateways that serve production traffic. Also, we ourselves own that gateway, so we were kind of the stakeholders of this first stage, so we didn't have to coordinate or interact with other teams. For this reason, during this particular stage of the migration, we decided to deviate a little bit from our requirements and to optimize for speed over safety. We decided to switch traffic over to Edge through a global DNS change. And yes, clearly that was a bit of a risky move, but we thought that being able to move quickly through this stage was actually worth that risk. This initial stage proved useful. So to a degree, it kind of showed that Edge was good enough for traffic, was battle ready. It also uncovered a bug in our XDots implementation, so we kind of fixed this before moving on to the next stage. The main objective of this second stage was to put some real production traffic on Edge. We settled on migrating the HTTP upstream for Spotify's web player. If you're not familiar with it, it's hosted at open.spotify.com, and it's what you would use to browse or play your Spotify music on Chrome or Safari, for example. Contrary to the first stage, we were now migrating a critical upstream that accounts for 5 to 10% of Spotify's traffic to HTTP services. Also during this stage, we now had stakeholders outside of our team and department. So first of all, the team that owns the web player, but also customer support. So what does this all mean in practice? Well, this second stage clearly was much more delicate than the first stage and required a well-thought-out strategy. We couldn't just simply wing it and hope for the best. The strategy had to optimize for safety, but still allow us to migrate at a decent speed. After some discussing and brainstorming, we came up with an iterative strategy that consisted in shifting traffic to Edge, shifting progressively more and more traffic to Edge, then monitoring and making any adjustments along the way if necessary, and then repeating until 100% of the web player traffic was moved to Edge. Since there were external stakeholders impacted by this, we also had to take into account some coordination work. But let's see how this happened in practice now. So this first diagram illustrates the setup for the web player on the old web gateway, so before any of this migration happened. We call the old web gateway WebLB, so that's what's in the diagram there. So in the top right corner, we have the web player upstream, which is configured to be exposed to the internet through the WebLB. In front of the WebLB, we have a Google Cloud regional TCP load balancer, proxying traffic to it. When a user types open.spotify.com in her browser, we want her to be resolved to the Google Cloud region that is closest to her. We use DNS GSLB to distribute traffic across different geographies. We write this DNS configuration and then have an internal tool that we use to push this out to our public DNS providers. So as I said earlier, our strategy was to progressively shift more and more of the web player traffic to edge. But this original setup couldn't really get us there. It needed some tweaking. So what to do? Well, we considered several different options, but in the end, the one that kind of fit most naturally with this setup that we had made use of the Google Cloud HTTPS load balancer. So let's see how we use that. In this second diagram, I have colored in blue the things that are either new or different compared to the original setup. So the very first thing we did is that we stood up an HTTPS load balancer in front of the WebLB and proxying traffic to it. It's the blue cloud that you see on the right-hand side of the diagram. To minimize risk, initially we modified our DNS GSLB configuration so that only Sweden would be resolved to the new load balancer, and the rest of the traffic would still go through the old TCP one. We ran like this for like a whole day, I believe, just to be on the safe side. And then once we felt confident, we updated once more the DNS GSLB configuration so that all the traffic will now resolve to the new HTTPS load balancer. So at this point, note that we still don't have any traffic going to edge. What I just described was kind of a preparatory step in that direction. So let's see what we did next. So first off, we added a new backend for edge behind the HTTPS load balancer. And so at this point, we had two backends behind them. We had one for the old web gateway, the WebLB, and a new one for edge. But no traffic was sent to edge just yet. However, in the HTTPS load balancer, you can configure a target utilization for each backend. This can be defined either in terms of CPU usage or RPS. We informally in our team call this configuration the capacity scaler. And basically, we effectively use this capacity scaler as a dial that we could use to either turn up or turn down the traffic that was going to edge. And the capacity scaler also doubled as our panic button because we could set the target utilization for the edge backend to 0, and that would route all the traffic to WebLB within minutes. So to recap the strategy, first, we stood up a new HTTPS load balancer. Second, we gradually resolved all of the web player traffic to this new load balancer. And lastly, we added an edge backend to sit behind this new load balancer and used the capacity scaler to gradually ramp up traffic to the new edge backend. Initially, we routed traffic to edge only during office hours. We monitored the performance of edge under load, and we tuned our alerts so that they would have sensible thresholds for things like resource usage or latency. We also created ping-dom alerts that would probe open.spotify.com for low latency and for availability, so that in case of issues with the web player, we would be notified and paged pretty quickly. After a few days of this dialing up and down the traffic on edge, we felt confident to leave it on 24/7. At that point, we trusted our alerts to notify us in case of problems, and also we had the panic button to get us quickly out of trouble in case we got paged at 2 a.m. or something. The second stage of the migration also went smoothly. We built even more confidence in the new gateway, and once more we discovered a bug in our xDOT service. So we fixed that before moving on to the last stage. So this was all good, but we now had another 130 upstreams to migrate to edge. So let's see how we tackled those. Vladimir mentioned earlier that the old web gateway had 25 different configuration parameters. Before just adding them to Edge blindly, we kind of took a step back and evaluated each config option in the context of a use case. If we found that there was no strong use case for a particular configuration option, then we just simply dropped it. Our main objective in this case was to keep the configuration API for Edge as simple and streamlined as possible. To give you a practical example, the old web gateway allowed exposure of both HTTP and HTTPS endpoints. However, we decided to drop support for HTTP endpoints in Edge as a way to encourage better security practices moving forward. Also, since we had a lot of upstreams to migrate, we wrote a Python script that would parse the configuration on the old perimeter and translate it to Edge configuration. The script covered 75% roughly of the upstreams. For the remaining 25, we relied on manual translation plus a process of peer review. Once the configuration were ready, then we were good to go. We just simply repeated what we've done for the web player, but this time on a bigger scale, because we were shifting the traffic to Edge for all of the 130 upstreams at once. You might wonder how it went. Well, Vladimir will cover that next.
A lot of things went well. Most importantly, we didn't cause any global HTTPS outage by doing this. The Gradle and staggered approach helped tremendously. None of us engineers in etc were paged during the night because of any Edge problem. But the panic button helped a lot. We used it at least 4 times, and it helped us. Yeah. We sent EdgeWent GA email just before Spotify Hack Week. That meant that we encouraged all Spotify teams to expose the Hack Week services on our new system. Spotify Hack Week is the time when Spotify is doing wild innovations. Like the Discovery Weekly is the thing that was implemented during a Hack Week, and the social listening is the thing that allows you to share the play queue with your friends to listen together. It's also started as a Hack Week. So after the Hack Week, we received a lot of praise that it was kind of easy to use our thing to expose services. Also, using Envoy turned out to be a good thing for us. There were bugs and inconsistencies, but we were never blocked, and there was always a way forward. So we didn't have a lot of experience before, but the docs are good, and we read the source, and our team members committed the pull requests and pushed them, merged. What is more important than successes? Failures, obviously. We had a few bugs and missed a few things. The zero-downtime promise was not fulfilled completely. Examples would be our Python script missed a few edge cases, and few services were overexposed. That meant that for a few days, we were, instead of returning 403s from the perimeter for some paths, we let the upstream backend handle it. Nothing bad happened, though, and it was later caught by automated vulnerability scanner and humans. I guess the other example would be that we missed a protocol. Somebody in the old gateway was using WebSockets, but it was like completely not clear from the reading the configuration. And our first version didn't support WebSockets at all, so I had to use the panic button to quickly shift everybody back. Our X-out service was unexpectedly overloaded, and we expected Google Load Balancer to handle it for us by shifting traffic back out of overloaded backends, but that didn't happen for some reason. And we dig into it, and turned out that we configured our Envoy to return 403 forbidden in case of any X-out service failure. And 403 forbidden is not a server error, it's a client error, and Google was not expecting to shift traffic in this case. So I guess the takeaway here is that you need to understand how the system behaves in case of the component's failures. Also, if we had a proper health check, it would also code it faster. So that kind of resulted in us returning 403 is forbidden for 10% of HTTP traffic for 30 minutes until we stopped the load test. So there is a software entropy, it doesn't make things easier. And the whole system had a lot of entropy. There were sites that were exposed but not used, and there were like 30 of them. I'm pretty surprised that the number of sites is too low. Also, there was features that were used by tiny fraction of websites, and also, for example, features like WebSockets were used, but they were not explicitly advertised that they're being used. So I guess the takeaway here is to design for entropy, design against the unused things like features and websites, and design for explicitness. We see big things ahead, but in short term, we are fixing some leftovers in the big migration and investing in reliability. So I guess after that, we would invest on supporting more X-Z authentication schemes. Like there are lots of in Spotify. We're going to, we need rate limiting, but our old perimeter, part of it's already support rate limiting, and if we want to unify the perimeter, we need to unify rate limiting too. We want to also invest in automated mitigation against bad deploys. That means that we have like lots of tests. We are also going to have canaries, like we have one canary, but eventually we would need to shard our perimeter so that we could deploy the changes very gradually. And now to more long-term plans. Our more long-term vision is to unify perimeter like a dream under one awesome gateway, and possibly one protocol, gRPC over HTTP3. We also want backends and clients to be one big service mesh, and to edge, for edge to handle all the types of ingress and egress traffic. Our X-Auth service, as you remember, it does the authentication and geolocation. We want to move the geolocation into a native Envoy filter so that the X-Auth service would be much simpler and has less responsibilities. We also want Spitfire developers to have declarative infrastructure. So I guess it's a thing now, and yeah, we want it. So the future of the perimeter is bright. And Erika, what would be the takeaways?
Yeah. Just before concluding, we wanted to share the 4 key takeaways from all of this migration work. So the first one would be expect things to go wrong. Sorry, I pressed the second time. Expect things to go wrong and be prepared for it, most importantly. So if you're migrating at scale and adopting a new technology that you're not familiar with, as was our case with Envoy, most likely you will bump into problems along the way. If on top of that, the stakes of the migration are high, then definitely you want to have a way to roll back to a working state. So the takeaway would be invest in a good panic button, and also think about how granular it should be. Would a global one be enough, or do you need a per service one? A second key takeaway would be work iteratively. Start small and possibly non-critical, maybe fail, quickly learn and adjust, and then go progressively bigger and more critical. This helps a lot when you are migrating a big number of services over the span of a few months. It allows you to quickly learn about the new system you're migrating to, and also to uncover bugs while minimizing the impact on users. A third key takeaway is look for opportunities to reduce the migration surface. This is especially relevant if you are migrating away from a legacy system that has been around for some time, and has evolved in weird ways over time. Identifying elements that in this legacy system that are no longer relevant or are not used, and doing this early rather than late in the migration can really put things into a different perspective. And finally, when we started all this migration work, we thought it was very daunting and scary. But it turns out that giving yourself room to fail and having a reliable panic button to get you out of trouble makes the whole thing remarkably pain-free and, weirdly enough, kind of fun. All right, so this is us. Thank you very much for taking the time to listen to us today. We're badly out of time, so if you have any questions, feel free to approach us, and we'll be happy to chat about this topic or even Envoy in general. Thank you.
All right. Cool.